Hello, I'm Sébastien Maitenaz, and I will talk about the fabrication of a truss-like beam, which was casted with 3D printed clay molds. This work is part of my PhD thesis, which is held by the Navy Laboratory, and which is a collaboration with a structural design office from the Vinci Group. So the goal of this conference is to talk about the future of construction, but I think it's always interesting to also look back at the past to understand how the choices that were made by our ancestors had an impact on our daily routines on work sites, and so to understand how the choice we will made can have a positive impact for the future. In my thesis, I mainly focused on reinforced concrete, so I will do a very short introduction on the history of reinforced concrete. Reinforced concrete is both a material and a constructive system that was developed at the end of the 19th and beginning of the 20th century. And at the time, it was a real revolution in the way we built, because we went from a craft construction that was dominated by very skilled but few workers to a much more industrialized construction with low skilled but a large workforce. And this industrialization was symbolized by the fact that for the first time, machines started to appear on construction work sites, machines such as concrete mixers, for example. But since 1950s, there hasn't been a lot of evolution in the way we build with reinforced concrete. And this is materialized by the comparison of machines that were used at the time and that we still use nowadays, such as rebar benders, concrete mixers, and concrete vibrators that look very similar. So there has been very little evolution. And the issue with that is that the construction methods and the tools that we use are not adapted anymore to the products that we produce, so buildings, which are higher, that requires to carry heavier loads, and so on and so forth. And there are many consequences from this observation. And in my thesis, I tried to address two of them, which is the lack of productivity of the construction industry and the lack of security. One statistic that you might know is that in France, there is about one death per day each year on construction work sites. And at the Navy Laboratory, what we believe is that digital fabrication is the right tool to address simultaneously those two issues, because by its very nature, it allows for better management of the flow of information, which is one of the limiting factors of productivity, and for better control over what we do through robotics and automation, for example. And control is essential to improve risk management. So in this presentation, I will try to show how we apply this principle of digital fabrication for the fabrication of an truss-like reinforced concrete beam that was casted with 3D printed clay molds. The presentation will be in two parts. In the first part, I will show how we treated the information through the whole design process, so from the calculation to the fabrication of the beam. And then I'll try to discuss what robotics requires in terms of design to be able to manufacture, or at least to ease the fabrication of such elements. So let's start with the management of information. Here you can see the whole framework for the management of information from the design requirements to the fabrication of the beam. We'll focus on the design elements. So the beams that we manufacture are calculated from the traditional Eurocode 2 calculation plus the strut optimization method that we developed during the thesis. And this optimization scenario is embedded in a C# solution, which main classes is a beam class, which includes all data that is required for the calculation. So design data such as the external geometry of the beam, the span, the section, support condition also, properties regarding the material or the section, to output of the calculation, such as a rebar cage. So in this class, we will include all the rebar diameters and the position of each rebar, be it longitudinal rebars or shear rebar, for instance. And this C# solution is embedded in a Grasshopper plugin. This enables us to have a better user experience. And so from within Grasshopper, we are able to manage both the calculation of the beam, but also to prepare the shop drawings. And those shop drawings will be the inputs to generate toolpaths, for instance, for the robot that will print the 3D clay molds. So the generation of those toolpaths is outside the scope of this presentation, but you must know that we did it using the HAL plugin, which is developed by HAL Robotics. And I decided not to present it here because I think that in this session, there is a presentation on this framework. So I will now concentrate on the simulation of the fabrication and the fabrication itself. So from the toolpaths that were generated, we are able to make simulations of the fabrication. And this allows us to, for instance, to check whether or not the space in between the clay molds will be sufficient to let space for the extruder. And if it's not the case, we are able, thanks to this whole framework, to modify the spacing in between the clay molds and to adequately modify the calculation of the beam so as to make it fabrication aware and to generate new toolpaths and new simulation. And once everything is checked, we can launch the fabrication. And here is a short time lapse of the 3D printing of the clay molds directly on the loss casing of the framework. The framework was firstly calibrated, and once this printing step is finished, we are able to pour sand inside the clay molds and then to pour concrete in between the clay molds and the wooden framework. So thanks to this whole process, we were able to successfully manufacture 2 prototypes. One that was manufactured about 2 years ago with 3D printed concrete molds because we didn't have the ability to print clay at the time. And then the second prototype, which the time lapse showed, which is very similar but printed with clay molds. So we've done a lot of mistakes in building the first prototypes, and I will explain what they were and to see how we were able to improve the whole fabrication process in order to manufacture a proper beam. So firstly, there were large tolerances on the placement of the rebars inside the rebar cages, and this is because the rebar cage was assembled by a non-specialist workers on the construction site, so in a not controlled environment, and nothing was checked on the geometry. The second thing is that in the design, we only managed to have a very thin struts. So the struts are the concrete diagonal parts. So they were too thin to let a coarse aggregates pull from to the bottom of the framework. And we also prepared an ordinary concrete over which we have a very little control, especially regarding the rheology. So the concrete was much too dry, and those 3 elements together result in this beam, which presents a lot of caking, and this caking doesn't enable to have a proper durability of the beam. Firstly, there is a bad transmission of forces from concrete to steel, and the steel is not protected from corrosion. So for the second prototype, what we've done is that we had the rebar cage fabricated by a specialist in a factory, plus the rebars were welded together, so they didn't move during the manipulation and during the transport of the rebar cage. So we kept the precision throughout the process. We also changed the design of the beam. So in order to keep the same structural efficiency of the strut, we decided we had to keep the same section. So we decided to reduce the width of the beam in order to increase the height of the struts to have sections that are more square. And so that enables us to have a better pouring. And we use a self-compacting concrete so that we didn't need to vibrate the beams in order to pour the concrete evenly. And as a result, we were able to manufacture a nice 3-meter long prototype. So as a conclusion to this talk, we just wrap up by saying that we were able to successfully implement this whole complete framework for the fabrication of the prototype. Of course, it is still very limited because we are only able to manage a simply supported beam with one span, so we should extend it for to a whole structural calculation. And regarding the fabrication, I think that the next step is to automate the fabrication of the rebar cage, because even though we had a better precision in the second case, it's still a limiting factor. And by automating the whole process, I think we will be able to have nicer results. So I think the conclusion is to say that it is what we try to do is to shift complexity towards upstream processes in order to ease the pouring of the concrete, which is the crucial task in order to prepare sound structural elements. So thank you for your attention, and I am ready to answer a question if you have some.